welcome to the second talk in our colloquium mini-series on thermalization and equilibration dynamics in quantum and classical many-body systems, hosted virtually at Washington University in St. Louis. So today it's my great pleasure to introduce Ehud Altman as our speaker, who is known to all of us as a leading expert on many topical issues at the interface between quantum many-body systems, cold atoms, and quantum information theory. So Ehud received his PhD at Technion in 2002. And after that, he has held several prestigious postdoctoral positions, namely at Harvard and at the Weizmann Institute, where he also became an associate professor at Weizmann in 2011. From 2012 to 2013, he visited Berkeley as a Miller visiting professor. And in 2016, he joined the faculty of UC Berkeley for good, where he has been a full professor since. Ehud has many broad interests in equilibrium and non-equilibrium properties of quantum many-body systems. He is, among other things, an expert on many-body localization, thermalization, and the role of entanglement in quantum matter. His work has earned him numerous prestigious awards and accolades, including the Yigal Allon Fellowship, the Young Investigator Prize of the Israel Physical Society, and the Krill Prize of the Wolf Foundation. So clearly we are extremely fortunate that Ehud is able to join us today and speak about phases and phase transitions of information flow in quantum circuits. Thanks so much, Ehud, again for being with us today.
Thank you, Alex, for the nice introduction and for inviting me here. Hopefully at some point I can come in person. I'm going to talk about a recent interest of mine in quantum circuits and the relation to thermalization and to quantum information. A lot of what I'll talk about today is based on work done with, I'll give a much broader talk, but a lot of what I know about it, I learned from working with my student Yimu Bao and postdoc Sunwon Choi, among many other people, but they deserve special thanks. And I'll cite some papers along the way. So the basic question I want to ask is concerns the difference between thermalization in a classical system and thermalization in a quantum system, whether there is a sharp difference and whether or it's just a crossover associated with some decoherence. And to make this, I need to explain a few things in order to make the question sharp. So first of all, I want to consider classical thermalization. I wanted to make a embedded movie here, but I somehow couldn't do it. Maybe I did it too late. Maybe I can switch. I'm not sure if Zoom will let me to switch to Chrome and show something. No, you don't see my Chrome screen, right? No.
I believe we do not, no.
Yeah, okay. Well, I probably need to reshare. Never mind, let me forget about this. Anyway, I'll start the show again. Well, my point is, this is a nice demonstration for statistical mechanics of molecular dynamics, and I'll tell you what it shows. It shows many particles. Their colors correspond to their velocities or speeds. And the system starts in a very well-defined state. It looks almost like a crystal, but then you turn on the heat, meaning velocities of particle, distribution of velocities, and very soon you see that the state basically evolves in time and samples all the space, phase space ergodically. Well, you see mainly real space, but if you look at the velocities, you also basically see the entire phase space. And you see from time to time, you see a state that is random, changingly random from time to time. That's basically the essence, broadly speaking, of classical thermalization. Now, the underlying equations in this case are completely reversible, but if even in the simulation, if you actually try to turn time backward, and you can, you find that it doesn't perfectly turn backward, actually not even remotely turn backward. And the reason is due to chaos. So basically, chaos gives you effective irreversibility, and a nice way to see it is illustrated in the right. If you start with some distribution, an ensemble of systems in phase space, then after some time, that distribution starts to grow. It conserves its volume, but it becomes more and more complex in a way that can be quantified by an entropy, Kolmogorov-Sinai entropy. And that's the essential way that you get information that irreversibility and thermalization in a quantum system. But the point is that at every point in time, if you look at a single system, the instantaneous state is very well defined, and all the information is encoded locally in the coordinates of the particles and their velocities. So you can observe the system and you can know its exact state at every time. Now, quantum thermalization is different than that. So here is an illustration of what happens in a quantum system of spins that thermalize. Initially it could be in a very well-defined classical states where all spins have been measured, but from this point on, it starts to propagate in unitary evolution. What the unitary evolution does, it starts to entangle the spin. So initially you get entanglement only of nearby spins, and the entanglement entropy, which is if you take a subsystem here marked by A, and you take the reduced density matrix of that subsystem, you can find the von Neumann entropy, and the von Neumann entropy is known to, is of course expected to grow in time. It's understood now that it grows linearly in time. Because initially you create bell pairs, if you want, correlations across the wall of the subsystem, the boundary of the subsystem. And as time goes on, you create more and more correlations in the system. And in the end, the unitary evolution transfers all the information that was encoded in very local, in single qubits or local degrees of freedom, into increasingly non-local observable, non-local degrees of freedom that, being so non-local, are really unobservable. And this is the essence of irreversibility in quantum systems. Although it's unitary linear evolution, the information flows from observable degrees of freedom to effectively unobservable degrees of freedom. So this information is effectively lost. And at the same time, as I said, the entanglement entropy, which is a measure of how non-local the correlations are, grows to a volume law. Okay, and in the thermal system, you expect it to go to a volume law with a coefficient equal to the entropy density at that temperature. If there is energy conservation, if there is no energy conservation, it just goes to the maximal possible entropy, which is the number of degrees of freedom per site, log of the number of degrees of freedom per site. It's basically the maximal entropy per site times the volume. That's what it goes to, which is like infinite temperature, if you want, if there are no conserved quantities. Okay, so to summarize this important point, the difference between classical and quantum thermalization is that in classical system, the state becomes random from one time to another, but all information is encoded locally. While in quantum system, the state becomes effectively a random state in the Hilbert space, and property of a random state in Hilbert space, for all practical purposes at least, is that almost all information is encoded non-locally in basically coefficients of a huge superposition of classical non-entangled states. So information is encoded non-locally. Now you can ask the question, how this is a very, very idealized picture of a closed system, unitary Schrödinger time evolution. Now you can ask, how is this picture affected if there is some observer looking at our system? Now, of course, for the classical system, I already told you it doesn't matter at all. If the observer doesn't change, it doesn't make such a huge back reaction with his observation, it's basically no problem for the classical system. But in the quantum system, as we know, measurement is a very fundamental thing. It makes a very fundamental difference. It can make a very fundamental difference. So the most extreme case is if the observer observes, so if he or she observes all the spins at once, if they're able to observe all the spins at once, they immediately collapse the wave function to some random state in the basis of observation, right? That's what we know from quantum mechanics. So basically, if we had non-local correlations, they're completely destroyed at this point. Every time we observe, we completely destroy the non-local correlations. So if we had a quantum evolution of a state, which here is sort of sketched as sum over classical paths, every time we observe, and these vertical lines correspond to observation, I think of them as observation points, you collapse the state to a particular classical configuration. So what we see effectively is, what we have basically is classical thermalization. There is no information left about the initial state in any non-local correlations. So basically, by observing all the spins, we have transformed from quantum thermalization to essentially classical thermalization, which, as we said, is basically a random state at every point in time. But realistic observers are not so observant. They can't see all the spins at once. They can measure maybe a fraction of the spins at a time with some, for example, they could measure every spin with some low probability P per unit time. So at every time step, you only disentangle some spins, but a lot of the other spins still retain non-local correlations, and then the system continues to evolve and you observe again some spins, and it's not clear what happens and whether eventually you disentangle or not. Now, at this point, I want to make an important digression. When I talk about observation, clearly the system is not completely closed now. It has an external observer, and the dynamics is not unitary. So I want to digress and say an important point, that there are two kinds of non-unitary quantum evolution that we know. One of them, which is the more commonly addressed kind of non-unitary evolution, is a system coupled to a bath. So this is my bad illustration of a system coupled to a bath. And this is the description of usual decoherence processes, for example. The system basically gets entangled with some environment degrees of freedom. So if I start with a pure state, I integrate out the environment, I have a mixed state because of the entanglement with the environment. So a pure initial state generally becomes mixed in such an evolution. And we need some equation to evolve the density matrix. And one such equation that's very useful and valid for certain kinds of baths, for example, Markovian baths, is the Lindblad equation. It's an equation for evolution of the density matrix. However, in this talk, I'm going to talk about a completely different kind of non-unitary evolution, which is the evolution of a monitored system. In a monitored system, the evolution is basically if you start with a pure state, it's an, oh no, it's my, I don't know what to do. If you start with a pure initial state, I have a problem with my,
I can't mute you.
Yeah. So let me mute my my phone here. It's a mistake. Okay. Okay, done. Sorry. I can return to this now. Okay. We're back. Yeah. So this is an important point. In a monitored system, if I start with a pure state, the state remains pure because there are two kinds of evolution. There is unitary evolution, and from time to time I measure, and according to the Born rules, what happens when I measure is I project my state onto one of the possible measurement outcomes, one of the eigenvalues of the measurement operator, but that's a pure state. It's a projection on a pure state. It's not unitary, but it's a projection. So really, the time evolution then is described as an ensemble of possible pure state trajectories, right? For every set of measurement outcomes I can get, I have some trajectory. Okay, that's really important and very different from the case of a bath. Now, in this case, for this to really be a monitored system, the observer must keep track of the measurements and somehow use the information they gained from the observation. So what does it mean the observer has to use it? Well, if they don't use it, and discard, basically they effectively discard the information. If they discard the information, they're no different from a bath. In this case, we're basically back to type 1 of non-unitary dynamics, which is a bath. Now, how can an observer make use of the information? There are two ways. One is because they have the information of particular measurement outcomes, they can post-select and, for example, wait until they have, if they want to test something that they need several copies of the same state, they need to wait for having several times the same set of measurement outcomes. Then they know they have the same state. And for that, they need to use the information of what were the measurement outcomes. If you have several copies of the same state, you can maybe measure some expectation value in a particular trajectory, right? But if you discard the measurement results, you can't do that. So post-selection is one way. It's hard because if a system is big, you will need to wait a very, very long time, exponentially large, in the number of measurements until you get the same results back. But anyway, that's what you have to do. Or there is another way, which is to use the information in order to feed back on the system. So these are the two ways you can use the information. But in any case, I'm going to talk about observables that actually make use of this information. So they actually require either post-selection or feedback. And in the simplest case, we're going to talk about post-selection. Okay, so after that digression, again, the main question is what is the effect of the observer? And again, the issue is that although the observer disentangles some spins, they're not disentangling the entire system. And you can ask whether eventually they will disentangle everything and the state will collapse to an effectively classical state. Or alternatively, is there going to be some non-local information preserved, encoded in the system? In other words, is there a sharp transition between quantum and classical thermalization? And one can ask a related question from a slightly different perspective, which is how fragile is large-scale entanglement? We all know that Schrödinger cats are not roaming the streets, and that's because they are really fragile. So the entanglement in a Schrödinger cat is really fragile. You make a measurement of one of the hairs of the cat, and immediately you collapse the cat. into one of its two states. But massively entangled states of the type that we're talking about here are very different because almost all the information is encoded not in the hairs of the cat, but in some non-local coefficients that are very difficult to draw. Which means that, if we measure just local spins or local hairs, we're not going to gain much information about them and therefore almost not collapse the state at all. So massively entangled states could be much, much more robust to measurement than Schrödinger cats. And the question how much is basically what we want to discuss. And there is also another question, can we ever study such questions? And fortunately now there is a big boom in building and designing quantum hardware, basically circuits that are aimed at eventually doing quantum computing. But meanwhile, until quantum computing comes along, I don't know, 50, 100, 500 years from now, we can use these systems to do very interesting physics. So here is an example of such an experiment, a very famous experiment by Google showing quantum supremacy using a programmable superconducting processor. This is their paper from Nature, in which they, I think, made two big achievements. First of all is massive entanglement, and second is a massive author list. Can compete with high energy physics already. But it is really, joking aside, it is really a very nice paper from the scientific perspective. And I want to describe it for 1 second. What they had in their hardware is basically a chip with many order 50 qubits coupled by basically by some couplers. Qubits are superconducting qubits. They're coupled by couplers, which they can say are programmable gates. They're different, and they can be different at different times and different positions in space. And then time runs to the right here. They apply the gates one by one on this system. And after some sufficiently long time evolution, they measure everything. They measure all the qubits, and they do that, they repeat it many, many times. And the idea is that this experiment, if you sample out of this machine, it gives you a sampling that cannot be obtained by any device that only has local information. So basically, I'm phrasing it in another way, but basically the sampling of this probability distribution is a telltale of having non-local encoding of information by this unitary circuit. And this cross entropy benchmark fidelity is the benchmark that if it's non-zero here, it means that they still have some non-local correlations. So basically that's what they show here, that even that they basically after some sufficiently long time still have non-local correlations in their system. And I'm not going to dwell on this a lot because I think you have an experimentalist coming. There are other platforms that have done extremely interesting, and they are not called quantum supremacy, but these guys have done not less impressive and sometimes even more impressive stuff to show that there are non-local correlations. For example, I think you're getting a talk in this series from someone in Marcus Greiner's group on cold atoms, and probably they will show you that they have measured how the entanglement entropy indeed grows as a function of time in such a thermalizing system, which is a really beautiful experiment. And there are really beautiful experiments in Rydberg arrays in Misha Lukin's group and in Manuel Andre's group in Caltech, which is also a very controllable system, and one can think of it as a quantum circuit, maybe not as programmable as the one in Google, but at least for doing interesting physics, it really doesn't matter so much, and it can be bigger and probably with less decoherence. And trapped ions are another very interesting platform like that. So all these systems present a new paradigm for quantum many-body systems, and they enable to do the kind of experiments that really start to ask deep questions about how a system thermalizes, how information is encoded in the system, and so on. Okay, so these are really experimental hardware that people is using, and now I'm going to talk about a useful theoretical model for all these systems. And I'll call them hybrid quantum circuits. They're not exactly like what I had before. I showed before in these experimental systems. They're systems built of there is an array of qubits, and as a function of time goes upward here. It is propagated. They're evolved by unitary gates. These are unitary gates. The unitary gates are random from one point to another and from one time to another. And in this model. And also we occasionally do measurements, single qubit measurements, or some local measurements on these qubits, which are applied with some probability p. So on every point, I could either apply or not apply the measurement with some classical probability p. And then once I apply it, the wave function evolves according to the Born rules, namely it's projected on one of the possible measurement outcomes, okay? Again, I want to make two remarks. First of all, there are three sources of randomness in this model. First of all, it's the randomness in the unitaries, the fact that they're random unitaries. Second, it's the random location of where we decide to do measurements. And third is the randomness associated with the measurement itself. Now, the first two sources of randomness are not fundamental. They don't have to be in the circuit. We can easily eliminate them. It turns out they don't matter much for how the thermalization is carried out. The third type of randomness, which is the randomness in the measurement result, is truly fundamental. It's not something we can change. It's really basic quantum mechanics. We can really think of the randomness in the circuit, like the randomness in the unitaries and the measurements, as some quenched randomness. And in a particular lab, it might be a particular realization. And as theorists, we want to look at the generic system, basically the ensemble of all the labs in the world. But even in a single lab, one cannot escape the randomness associated with the measurements. And second is what I said before, this evolution is not a simple coupling to a bath. We are going to be interested in observables that are sensitive to the actual log the experimental has of the measurement results. And the state in each of trajectory like that, if it begins as a pure state, it remains pure at all times. Okay, so oops, there is something missing here. Okay, so one nice measure in such a quantum circuit of non-local correlations is, of course, the entanglement entropy of the subsystem. So that's one of the first things people wanted to understand. And I'm defining this property average of SA, where SAM here is, A is a subsystem A, for example, half the system. And in a particular trajectory of measurements, particular set of measurement outcomes, given a particular set of measurement outcomes, I have a specific state psi. I can calculate the entanglement entropy for that particular trajectory, and then average over all the possible trajectories with their probabilities, which, as I remind you, is fundamental and depends on the state itself. And then after the fact, also average over the unitary U. Unitary gates. And how do we expect that the S will change with time if we increase the measurement rate? So as I told you before, if we don't measure at all, we expect this blue curve, we expect the entanglement entropy to grow linearly with time until it saturates at the maximum possible value, which is a volume law proportional to, length of the system A times log 2 if these are qubits, okay? On the other hand, if we measured at every point, or almost every point at every time, then we would expect an area law. So the system rises, the entanglement entropy rises a little bit, but then saturates to a constant in this case for a one-dimensional array, so it's a constant. Okay, so, and what happens in between? How does the system go between these two extremes? So there has been recently very nice numerical evidence for a phase transition between these two extremes. So there has been the first two papers were on these numerical evidence were by Adam Nahum and collaborators in 2018 originally, and Matthew Fisher and student and postdoc in Santa Barbara basically appeared simultaneously. And here you can see the simulation from one of these papers, which did massive large-scale simulation using Clifford circuits, which are simulable classically, and therefore they could go to pretty large sizes. Here it's more than 500 spins in this kind of circuit. The unitaries are not generic unitaries, they're Clifford gates, but it turns out that for some aspects, it doesn't seem to make a difference. It's an interesting question on itself, but what they see here is what I showed you before. There is area law for a very large rate of measurement. For small rate of measurement, you see that this is a function of A. You see at the size of the subsystem A, you see a very clear volume law, and there is some separatorics in between, and when one does the scaling properly, you can really see a critical point. Everything looks very nice. There is a critical point between having area law and volume law entanglement between classical-like and quantum-like thermalization.
So very naive question. Should I think of P as temperature effectively in some sense?
Okay, it's a very good question. Here, we don't know of any why you would think about it as temperature, but as you will see, there is some effective model in which you can think of P as tuning a temperature. That's right. What is the high temperature phase and low temperature phase here? All of this is, of course, out of equilibrium. There is no real temperature here. Why is this like a temperature, and how is this phase transition? Is this phase transition really behaving like some classical statistical mechanics phase transition that we know or not? That's actually still an open question, but I'll show you a way of how to begin to address it in a few slides. And also why P becomes like a temperature here. Yeah, so far it's just, it's just numerical evidence. Well, there is some anticipation that there are two extremes where there is very different behavior. Maybe there is a phase transition. And, they went ahead and tested that, and they can see something that looks like a phase transition. They can scale the results in a reasonable way, and basically what they show here is the entanglement entropy minus the entanglement entropy at the critical point, which they fit, as a function of P minus the critical P, and then the x-axis is scaled in the usual way with some exponent, critical exponent nu. So yeah, that's what they did. What is going on here? Sorry, this is not supposed to be here. Yeah. So although there was a transition, at least early on, it was a bit puzzling, and there was an argument for why, or at least naively, one would think there might not be a transition, because naively, the transition is some competition between unitary gates that entangle your system and measurements that disentangle, right? Because every time I measure, the spin that I measure becomes disentangled from the entire state, right? Because it's now in a well-defined state. It's in a definite pure state. So clearly it's not entangled with the rest of the system. So one can write a naive equation for the change of the entanglement entropy after a time step. And the change of entanglement entropy is across this interface is basically log 2 at most, because the unitary cannot change the entanglement by more than log 2, and unitaries that act away from that line, not across that line, cannot change the entanglement entropy. On the other hand, if I measure with some probability p, then on a time step, I'll measure n times p spins. So I'll remove n times p entanglement. So I'm increasing the entanglement by something of order 1, and I'm removing extensive entanglement. And the only steady state for such a rate equation is basically no entanglement, or no entanglement of order 1. I cannot have a volume law entanglement for that kind of rate equation. So that was kind of a puzzle. How do you nevertheless get a volume law? How come the system is not eventually completely disentangled by the measurements? Well, because there is some fallacy here. There is something more subtle going on, and that has to do with the fact that the measurements are now trying to reveal information that is encoded non-locally. And to understand that, one can take a toy model where we have two systems that are entangled with each other by basically, for example, sharing gamma times n bell pairs. So there is volume law entanglement between these two systems. This rainbow basically, in the usual way you sketch these things, basically symbolizes sharing of n gamma times n bell pairs. Then you take the left side and evolve it by a scrambling unitary operator, some big unitary. And you can also do it to the right side. As we'll see, it really doesn't matter. But crucially, then you measure locally a fraction p of the qubits on the left side. It doesn't matter which ones, because anyway, you randomized everything with this unitary. You measure it, and now you can ask the question: the fact that I measured Pn p times n spins, does that immediately mean that I will remove entanglement p times n from my initial entanglement gamma times n? Is that true? And one can show that this is wrong. This is not true in general. In fact, if U is completely scrambling, then local measurements cannot reveal any information up to some corrections of order 1 over the Hilbert space dimension, any information on correlations between this subsystem B, which is not measured, and C, which means that whatever entanglement was between them, these cannot reveal, and therefore all these correlations remain completely intact. Because one can also there is a simple way to understand it, that if this is sufficiently random, it becomes like an infinite temperature state. If you measure number of spins that the measured system is smaller than the half of the entire system, then really it becomes like the rest of the system becomes like a bath, and is completely and the system that remains becomes like an infinite temperature state, which has no correlation. So C and A, for example, become non-correlated because they together can be thought of as thermalizing, as being thermalized. So all the correlations are between C and B. Anyways, this can be proven rigorously in some modified version of what is in quantum information called the decoupling inequality. Now, what we understand from this, by the way, this unitary here was completely unnecessary because it didn't change the entanglement. I can just remove it. But if I remove it, you see I can change these lines, and it looks basically like I have just an input state here. And the idea is that I can insert an input state which is entangled with some reference, and I can ask, so there is some information about correlations between the reference state and this input to my system, and you can ask how much of this information remains. And the entropy at the output is really the amount of information retained on the correlations with the reference. So the volume law phase, basically in this way of seeing it, is really like an emergent quantum error correcting code, which is protecting information by scrambling it enough. And then the measurements are not able to extract this information, and therefore the volume law is stable. So the volume law is a stable quantum error correcting phase. That's another way of seeing it. And this was basically pointed out by our paper, and then there is a related paper which shows that this transition can be thought of as a purification transition. If you start with a mixed state, then the output is going to be pure in the area law phase. It's going to be still mixed in the volume law phase, and the being still mixed here means that the initial density matrix encoded some unknown information. That's the mixed. That's why it's mixed, and the output has finite entropy, means that there is some information remaining. No matter how long, so the remarkable thing is no matter how long I run, I can, if the system is wide enough, namely if it's infinite size, then I can run it for infinite time and still retain all the information, no matter that I'm measuring it all the time. So I measure for an infinite time, but I can never reveal all the information. Okay, so now I want to discuss, the last thing I want to discuss is mapping of this kind of hybrid dynamics of measurement and unitaries, basically mapping the thermalization process in a monitored system to a statistical mechanics model. And I should say that this had a history. So before people discussed observed systems, they were looking just at random unitary circuits. And there is a nice mapping to statistical mechanics of spins in random unitary circuits. And our paper, along with another simultaneous paper by Jan Romain Vasseur, Zhuang Yu, and Andreas Ludwig, basically generalized this mapping to the case of monitored systems, where the kind of non-trivial thing is that, yeah.
Interrupt you. We had a question in the chat. I don't know.
Sure.
Take that right now.
So is there, should I look at the chat or?
So Mariam Mudassar is asking, how do you reconcile these with the plots you showed earlier from, which showed a phase transition from quantum to classical as we did measurements?
Sorry, how do I reconcile what?
Yeah, Mariam, do you want
to? Maybe you can speak.
Yeah,
so I can.
Maybe you rephrase the question. So maybe I didn't get what you were trying to say. So over here, you showed that the volume law entanglement is protected by scrambling. But from the plots that you showed before, the volume law changed to an area law as you did.
Okay, so first of all, it's here I show that it's protected as long as there are not too many measurements. There is an inequality here.
Okay.
This is just a toy model, but even in this toy model, there is an inequality that actually makes sense and gives you some critical P. This is a toy model because all the measurements occur at the end of this unitary and not while you're scrambling. But still, it gives you a reasonable kind of estimate for this probability. So there can still be a phase transition, because if you're measuring too much, then another way to think about it is if you're interrupting this process of scrambling too much, then this unitary is not scrambling enough, right? So you're interrupting so it's a competition between scrambling by the unitaries and the measurements that do two things. First of all, they try to extract information, but they also interrupt the scrambling. If you interrupt the scrambling too much, then it's not scrambled, and then it's easier to get measurements. And there are two fixed points then. One where it goes to no scrambling, measurements are very effective. Another where it goes to scrambling, measurements are ineffective.
Okay, that's helpful. Thank you.
Yeah, good question. Thanks it helps me clarify. Okay, so now I'll talk about the mapping to statistical mechanics model. So before I map to statistical mechanics model, the mapping basically is based on what quantity we want to find. So the most natural quantities we usually want to look at in physics are expectation value of observables. But as I said before, in this case, they're not interesting, because if I look at an expectation value of an observable, basically I have to sum over all paths, and expectation values sum over all paths and over all trajectories. All trajectories, trace over this density matrix of the trajectory, and then average over the unitary gates. This is basically like taking the trace in the averaged density matrix, which is averaged over measurement results. I've discarded the measurement results. One can show easily that because the measurement operators are Hermitian by postulate of quantum mechanics, then this kind of, and it will give me a time evolution for the density matrix, a Lindblad time evolution, which is called a unital channel, or not Lindblad, Krauss evolution of a quantum channel called the unital channel, which has a fixed point as the trivial density matrix, one normalized by Hilbert space dimension. So basically nothing interesting could happen in terms of, if I just discard measurement results, then what I'll get as the average state, it's just going to look like an infinite temperature state. So I need some quantities that actually are nonlinear in the trajectory density matrix. For example, some fluctuations over trajectories. So these are all quantities that to measure, I'll need to acquire data and then post-select in order to be able to measure them. So they're hard to measure, but that's what you need. So moments of observables like this, for example. So you see they're nonlinear in the density matrix. One can play a trick and construct an object, which is not a density matrix, but doubled or an n copy of the density matrix. This is a new structure. If you have that, then you can actually think of that. These moments can be thought of as linear traces of this bigger object, which is a doubled density matrix. The simplest object, which is not a linear in the density matrix and requires such post-selection, is, of course, if we want to calculate the purity of a state or the purity of a subsystem. Because the purity is, I'll show it in the next slide, I think. Where is it? Yeah, the purity is trace of rho squared. In the end, I want to look at the log of the purity, and this is more complicated. It requires some replica limit, but let me not talk about the complications for here. You can ask me after, but if I want to calculate the purity, then I need to sum over different trajectories. Sorry, this can, in reality, this in this strange replica limit, there is squared here, but this is not supposed to be squared. But then I take a trace of rho squared. The probability is not squared here, but trace of rho squared. And if I look at trace of rho squared, how do I calculate that in reality? Well, I need to propagate rho squared, the square of the density matrix. It's in the subsystem A. So first of all, I need to take the density matrix twice. So psi, ket, bra, propagate the ket forward, propagate the bra with u star, ket again with u, bra with u star. I get in the end, the doubled density matrix, which is just a pure double density matrix. It's just a pure state replicated 4 times in this case because of ket bra. And now, in order to calculate trace of rho squared, I need to first multiply rho. First of all, I need to calculate rho of A, which means trace out system B. So I need to, the trace out is basically signified by connecting ket and bra of in system B. And then I have to multiply rho A that I got by itself. And these contraction of indices of multiplying matrices, you can easily convince yourself is basically in tensor notation connecting the output of this to the input of this and so on, right? So you see that there is a different connection of the tensors created by this unitary evolution in the A subsystem, where I connect the ket of copy 1 to the bra of copy 2, while it's connect the ket and bra of the same copy in system B. I'll call what is going on in system B as identity, because it's just a name. It's because I take, I pair systems of the same copy, while I call swap what's going on the way I connect system B. So this is the way I should calculate the dynamics. It's in general very, very hard. It basically means contracting this large 2-dimensional tensor network, and it's as hard as calculating quantum dynamics. There is nothing really simple about it. By the way I draw this here in this tensor network is these blue parts just correspond to unitaries multiplied 4 times. It's this every local unitary I need to have u star to propagate the ket, the bra, the ket, the bra of the 2 density matrices I need to calculate rho squared. Okay, so this is an example of simple quantity that already depends on the measurement outcomes, but it's a very hard problem. Before showing how to simplify it, I want to show that there is an interesting dynamical symmetry here. And you see it, it's almost trivial. There is a global symmetry to permuting between kets and independently between bras. And this is simply because the dynamics preserves all the time 4 identical pure states. So globally, I have 4 identical pure states, and the double density matrix is simply made out of them. So because they're identical, of course, I can decide to take this one and move it to the other copy. So this is copy 1, this is copy 2. I can permute the 2 kets, of course, right? This is basically trivial. This is a Z2 symmetry, global Z2 symmetry, which is for the case of 2 replicas. If I have more replicas, there is a larger symmetry. There is a SN permutation symmetry of kets, SN permutation symmetry of bras, and then there is another Z2 time reversal-like symmetry, anti-unitary symmetry associated with replacing bra and ket, and exchanging ket and bra and complex conjugating. This is related to the fact that the dynamics retains hermeticity of the density matrix. In any case, here I'll just look at the Z2 symmetry because I'm looking at the simple case of 2 copies. So I just want to make sure you understand that this is trivial in the case of this dynamics because the dynamics preserves the purity of the state. and because the measurement outcomes, basically I make sure that there are two identical copies, means that the measurement outcomes in these two copies have been identical, right? In order to be able to measure something like that, I need post-selection to make sure I have two copies where I had exactly identical outcomes. But this is the post-selection. But if I instead had dynamics which was mixed, not keeping the system pure, then I had a mixed state, then I could not exchange ket and bra. You could think, if you want, is in this density matrix, the ket and bra are entangled, and if I move one of them to, if I exchange between them, I create a mess. I'll show another picture in a second. So in a mixed state, this doesn't work. And by the same token, this is the reason why this is a global symmetry, but not a local symmetry, because if I look at a single site or some subsystem, this subregion is not in a pure state by itself. Right, so if I exchange it, I again create them. I cannot, I cannot exchange the ket from one copy with another, because that site in particular is not in the pure state. I have to do it globally for the entire system. So it's a global Z2 symmetry that I have. Now let's see how this Z2 symmetry manifests. So it turns out that averaging, I said that contracting this tensor network is in general very hard, but averaging over the unitary gates makes it much, much simpler. What averaging does, it basically projects all these many degrees of freedom that are output from every unitary onto just a single degree of freedom, which is, if you want, it's like an Ising variable, and it indicates if the kets at that particular site are exchanged between the two systems or not exchanged between the two systems, swapped or not swapped. So you can think of it as a classical Ising variable, and contracting the tensor network is summing over all these configurations, all the possible wirings. Someone has a question? I see there is a raised hand.
I have a question.
Yes.
So, how do you deal with the normalization that you need to?
Good. Excellent question.
Yeah, because that's tricky, right? What do you do?
Yeah. So that's true. I'll show you in I think I have it in one slide. So in reality, the way you deal with the normalization is you always do it at the end. So you divide by the trace squared. So for example, I showed here that I calculate this. I actually do not normalize I leave a non-normalized state, and I divide by the trace row squared. So that means I'm going to divide by a partition function. So I calculate the Ising partition function. I contract this tensor network with these boundary conditions, and I divide by contraction of the same tensor network, but with the boundary conditions like in B, identity everywhere, which is the normalization. So in the end, I am going to calculate a ratio between two partition functions in order to normalize. And you'll see how it comes out. It comes out nicely. So let me show in a second. It's a very, very good question, but in the end, you can normalize at the end. And the idea here is to normalize at the end. Of course, doing this normalization for the purity is less of a problem. It's more of a problem if you want to do it for the entanglement entropy, which is the log of the partition. And then you have the usual denominator problem, and you need an extra set of replicas to solve that. So let me leave that aside. That's the reason why this Ising model, for example, does not really describe the true critical behavior, but it does describe a lot of nice things. So let me continue with it. So in the end, basically, the unitaries project onto a pair of degrees of freedom, And you can see the measurements basically change the couplings between these degrees of freedom. And if they're very strongly ferromagnetic, just with some non-generic couplings, ferromagnetics with weird non-generic couplings, when they're purely unitary, they become more like generic ferromagnet when you add measurements, and the strength of the coupling is reduced by the measurement. So basically, it's like reducing the temperature of this classical model. Again, contracting the tensor network is like summing over all the possible rewirings of the circuit with the swapping or non-swapping of Ketz and Braz on every site. That gives you a partition function for an Ising model. Remarkably, it's because of this averaging, it has no negative weights. One has to be a bit careful. You get negative weights, you have to integrate out a set of spins, then you get non-negative weights. It's not so simple, but there is a range of parameters where you don't get negative weights. So you get an Ising model, ferromagnetic Ising model with a tunable temperature, and a very interesting boundary condition. The boundary condition is basically fixing all the spins up on the top region and down on region A that you're calculating the entanglement entropy of. It's you fix down and you fix to up on region B. So if you're in the ferromagnetic phase, you see that you force a domain wall here, and this domain wall will cost you linear energy. It's a little bit more complicated. Note that I have to normalize. So basically, entropy, the entanglement entropy, not the purity, is the log of this, log of the partition function. It's basically the domain wall free energy, or free energy of the configuration with the domain wall. But then we had in the denominator, we had the normalization that Alocia asked about, and this is the partition function. This is log of the partition function without the domain wall. It's the free energy without the domain wall. So what I get in the end with normalization is just the extra energy cost of a domain wall. And in the ferromagnetic phase, this is exactly, this scales like the length of the domain wall to leading order. And in the paramagnetic phase, domain walls become cheap. They have a constant energy. And that basically gives you the entanglement of order L, volume law entanglement versus constant entanglement in the area law phase. Now, the intuition for the broken symmetry phase in the entangled phase is you can understand it in the following way. Look at just the Ketz of copy 1 and copy 2 in the case of an unentangled state, a product state. In an unentangled state, I can swap, since they're identical unentangled states, I can swap spins between the two sides. And if I only do a swap on a subsystem A, I don't do anything, right? I get the same state back. On the other hand, if I do the same thing to an entangled state, look, they're entangled but uncorrelated between them. When I do a swap, I basically create correlations between between copy 1 and copy 2, and I get something that is not identical to what I had before. So it looks like if I do a subsystem swap, I create a defect in the entangled state, and I don't create a defect in the unentangled state. And the longer the range of the entanglement, the bigger the defect will be. So that's basically the intuition for why one can understand the unentangled state as a broken symmetry state of this, effectively broken symmetry state of this dynamical replica symmetry. Okay, let me skip on that. Okay, I would just say it very, how much time do I have, if any? Alex, or?
Yeah, ideally you would soon wrap it up.
Okay. So I'll try to wrap up in a few minutes. I'll just say that once we have that model, we can easily identify other interesting signatures that are more natural to measure of the transition. And one particularly interesting one is we can ask the question, we say that this transition has to do with information. So we can ask, if I am an experimentalist and I see the log of the measurement outcomes, can I tell by this log if someone I didn't see, but some graduate student came to my lab and from one day to another made a small change to my initial state by applying some small unitary, unitary close to 1 on it. And so I'm measuring in day 1, I get some probability distribution of measurement outcomes. I measure on day 2, I get another probability distribution. There is a standard measure of the distinguishability between two classical probability distributions I have, which is the classical KL divergence. So I can calculate that, and that turns out to also have a replica 2 version, replica version, like a Rainy 2 version. And this Rainy 2 version is mapped again to the same exact same statistical mechanics model. Any replica 2 version object will map to the same thing, except the boundary conditions will be different. In this case, the boundary conditions in the top will be all up, and at the bottom, there'll be some small field coupling to basically a spin down. So in the end, this will be the free energy with the field on the perturbed site. It's basically like 1 minus magnetization. So I didn't write it clearly. So in the end, I should have written it. The KL divergence over the strength of the coupling, strength of the perturbation, is called the Fisher information. And that will be proportional to 1 minus the magnetization at the bottom. Now, if we have a broken symmetry state, because the top is up, the bottom will be up, right? We'll have finite magnetization because there'll be infinite distance correlation between the top boundary and the bottom boundary. But in the paramagnetic state, the effect of the top boundary will decay exponentially with the depth of the circuit, which is time, and I'll not have a magnetization at the bottom. So looking at the magnetization, at this something the experimentalist can measure, it's called the Fisher information on the initial condition, one sees that beyond a certain strength of measurement, basically it's saturated. It means that by measuring, the experimentalist can gain all the possible information on the initial state. As if he or she measured all the spins immediately after the perturbation was done. On the other hand, in the volume law phase, when the measurement strength is not sufficiently strong, you see that this falls below saturation. This is like the magnetization here going from 0 to something finite. And this means that there is some missing information, and that missing information that they can never extract has, again, to do with the fact that there is that it's protected information. It's encoded in some protected way, and you can see that very nicely in the statistical mechanics model. So the summary is that there is a sharp transition between quantum and classical thermalization. That's the answer to the question we posed in the beginning. It is a phase transition in the capacity of the system to encode information non-locally. And the patterns of information encoding can be understood simply by using a mapping to statistical mechanics models. Now, using these kinds of statistical mechanics mappings, one can get much more mileage and find many interesting connections. So, for example, in a recent paper, we showed that if you have not just a random circuit, but a circuit that has certain physical symmetries imposed on it, one doesn't have only in volume law phase and error law phase, but one can have a much richer classification of phases, which is controlled by some unexpected enlarged symmetry, which is larger than the symmetry of the circuit, because you need to compound the symmetry of the circuit with that dynamical replica symmetry. And that means you have multiple area law phases and multiple volume law phases that are characterized by various broken symmetries. You can also understand fermion circuits this way, and they have an interesting phase diagram related to emergent symmetries. More recently, we found that there can be some finite time transitions associated with onset of finite teleportation fidelity across infinite distances. And all of this can be described by a statistical mechanics model, But of course, there are also very many open questions. One of them that is not well understood yet is what is the nature of the critical point itself? Because while the phases can maybe be understood in ways that do not, where you do not take the replica limit explicitly, the critical point, you probably need to do that very carefully. So we still don't understand the critical behavior. Now, all of what I talked about were not really the most general types of circuits. They included only unitary dynamics and measurements. But in general, we're maybe even more interested than in systems where, in addition to that, you could have some decoherence processes, or let's say imperfect measurements where you lose some of the information about the measurement. And the question is whether there are some encoding phase transitions in such circuits. Now, in the entanglement, in the entropy, which is in the presence of decoherence, it's not entanglement entropy anymore. It's really just effectively could be classical entropy. There is no phase transition because you generate entropy by coupling to the bath. But there are other measures that try to find entanglement in mixed states. And the question is whether we can have such transitions of non-local information encoding despite coupling to some decoherence. Another question is whether there is a simple way to observe these transitions in the lab. Currently, this requires exponentially many repetitions because of post-selection. One can ask whether some of these effects can be, for some of these effects, we can trade post-selection for feedback in an advantageous way and see some of these effects. And finally, can we use the new insights to design or think of new paradigms for quantum error correcting codes? This is taking it maybe outside of my field, but probably it's also interesting. So yeah, thank you very much. If there are any questions, I'm happy to answer.
Well, thank you so much, Ehud, for a very interesting talk. And sorry, I had to rush you in the end. We had a few questions already during the talk. Is there maybe one or two more brief questions?
See a raised hand.
Yes, please.
Kazuaki?
Yeah.
Hi. Yeah. Thank you.
Hi, Kazuaki. How are you?
Yeah. Hi. Yeah. Very nice talk. So, I'm really interested in the connection to the Hamiltonian dynamics. So, in your very beautiful result, the random unitary circuit makes the more and more entanglement in the quantum system, and the information is delocalized.
Yes.
And but as you mentioned before, the yeah, I think the basic question is a quantum summarization problem. How can be connected to the classical summarization problems? And quantum summarization is mainly discussed in the usual quantum Schrödinger equation, closed quantum system dynamics. So so my question is, this kind of phase transition can occur even with closed, so Hamiltonian dynamics with continuous measurement?
Yeah. Yes. Okay. The answer
is.
I
understand that there's no answer here. So I want to hear your perspective on that. So.
Yeah. So my understanding is because once you add measurements, anyways, you don't have conserved energy. So the fact that you have Hamiltonian dynamics is not so important anymore anyways. Because you lost unitarity anyway by measurements. So I think in this case, having Hamiltonian dynamics is not essential. You can have it or not have it. I don't think it will make a big difference. If you have measurements. Of course, if you don't have measurements, it's a very different thing. Now, you can ask though, if instead of Hamiltonian, you have Hamiltonian dynamics where there are other hydrodynamic conserved quantities like charge conservation and these. So they're, in addition to this scrambling, there are also diffusion modes that interact with them. So we haven't discussed this, but actually there is very, very recently, Romain Vasseur and collaborators, they put a paper up where they discuss exactly this problem. I have to admit, I haven't read this paper carefully yet, so I don't want to comment on it here. If someone here knows it, but it looks like a very nice work on how to couple this to conserve charges. Energy probably cannot be a conserved charge here, but charge can. Yes.
I see. Yeah, I think I will check it out. Thank you. Yeah.
I see there is another question by Grace here. Yeah. Or you had.
Yes, Grace. Do you want to ask your question aloud?
Sure. Yeah. So my question was related to your comment about how the key thing for having this phase transition is the measurement outcomes being random. But like in Clifford circuits, a measurement outcome just manifests as a sign on the stabilizers. It doesn't like affect things like the entanglement entropy. So I was wondering, I guess, how to reconcile.
Wait. I mean, in Clifford circuits are still, from the point of view of the state, the measurement outcome is still, so in terms of the stabilizers, something is going on under the hood, it's true. But in terms of the state, the same thing still happens, right? It still projects and disentangles. So everything happens exactly as in quantum mechanics. Clifford dynamics is entangling. So entanglement grows linearly in time. State entanglement, not operator entanglement, but state entanglement is growing. So everything happens in exactly the same way as I described still in Clifford. You're right that under the hood, you don't have to calculate the state dynamics, you calculate Heisenberg evolution of stabilizers, which is achievable classically. So in that respect, now there is also an argument for why it would be similar, at least if you look at quantities like simple quantities like purity, because for that all you need is second moment. And when you average on second moment, it's called unitary 2 design. At that level, averaging over Clifford's is identical as averaging over Haar random, more generic unitaries. So at least for some aspects, they should behave the same way.
Okay, thank you.
Yeah. Alyosha, I think there is a question here.
Yeah, I know I already asked the question, but I would like to ask another one.
Yeah, sure.
So, first of all, great talk. And I really like this work. The way I see it, please correct me if the metaphor is wrong, is that here you have a competition between a kinetic term, which is the entangling unitary, and the potential that is localizing, that is the measurement. So it's a bit like a multi-insulator transition. So if this picture has any value, okay, and maybe it doesn't, but so let me propose this. You said that the randomness in the circuit and in the way you measure doesn't actually play any role, right?
The randomness in the circuit, I'm not saying it doesn't play. That's probably not completely correct. I mean, it plays a role. I'm not sure it's it's a good question. I'm just saying it's not as fundamental as it might change some subtle things. Yes.
Yeah. So I kind of agree with you. So let me propose this. Imagine that you are only evolving with the CNOT gates. Okay. So there is no randomness in the gates, but they're very good at entangling and at scrambling. And you always measure in the computational basis, okay?
Yes.
And you are below the transition, so you have below the critical P, so that you have volume law, okay? But just below, now you are just below. Now, you imagine that you add some randomness, like now you make the measurements in random basis, or you have the U's are actually random at that level of P.
Yes.
So would this randomness drive to a localizing transition as in many-body localization?
First of all, okay, so very good question. Let me answer it in kind of two layers. First of all, you're very, very right on this analogy to Mott insulator, and I mentioned this work on monitored fermion circuits. And on this work, and also on the other, I mentioned here a mapping to statistical mechanics, but you can imagine that if you have a mapping to statistical mechanics, if I made the time evolution actually continuous time, I could think of this mapping to statistical mechanics as, and there is a continuous mapping way of doing it here, a continuous time way of analyzing this problem. It's called Brownian circuit. In this case, instead of a statistical mechanics model, I could think about it as imaginary time evolution with a quantum Hamiltonian. And in this case, when you have local measurements on the fermion circuit, it actually is exactly like a Mott transition in one dimension. And that's why there is a U1 critical phase. This turns out for non-interacting fermions with measurements. So it's exactly that. So yes, and we actually even talked about what is the role of randomness, because here because we average, this is the average system, there is no randomness. But if we want to take a proper replica limit, we could, instead of averaging over measurement outcomes, we could leave them outside and look at them in this effective statistical mechanics model as U1 symmetric, in this case, some disorder that obeys the U1 symmetry. And one can ask whether in this critical point that disorder is relevant or irrelevant, and then decide whether it's, so it's a little bit strange kind of disorder, because the same thing that gives you the temperature also gives you the disorder. So you might get a special critical point that we don't know that yet because of this special connection between the disorder and the temperature. Sort of like maybe analogy would be if you know the Nishimori line in disordered spin systems. So I'm not sure that we'll get that, but there is a subtle role for the disorder here that we but one thing to note is that even if you think about it as the non-disordered model, as a quantum model, actually you have to revert back to the statistical mechanics picture when you think about it as true disorder, because it's space-time disorder. So really it's better to think of the disorder in the statistical mechanics type model. If you don't want to average over the disorder because you want to take some alternative to replicas, for example, then you have to think about it as, so for example, there have been nice works recently by Matthew Fisher, actually earlier by Adam Nahum, on thinking about these domain walls inside the, either in the volume law phase, as domain walls are like polymers in a disordered media, and then the measurements, you think of them as some occurring at some disordered locations, because you don't want to average over them still. And to understand the fluctuations of the domain walls better in the volume law phase. Yeah, so maybe I'm answering part of your question, but the disorder doesn't have a completely innocuous effect, but it's less fundamental effect than the intrinsic randomness due to the measurement outcomes in quantum mechanics.
Thank you.
Okay, I think it may be time to thank Ehud once more for a wonderful presentation. So next week, we will welcome Gil Refrel, and he will speak about topological physics at the light-matter interface. Hope to see you all again next Wednesday.
Thank you very much. Bye.
Bye-bye, Ehud. Thanks a lot. It was wonderful. Thank you.
Thanks.